Good morning and good afternoon. Welcome to ARA's webinar Wednesday. I am Sri Rao, your moderator for today's webinar titled Traffic Speed Deflection Device TSDD, Data Quality Assessment and Applications. Now, I would like to introduce our presenter, Dr. Ali Moravatar. Ali, a good friend of mine, is a senior payment engineer at ARA with over 8 years of experience in payment and geotechnical engineering, project management, and non-destructive testing technologies. He leads many national initiatives on TSDD data analysis and implementation and has supported DOTs in Illinois, Texas, Michigan, Ohio, Georgia, and Wisconsin. Some of you may know Ali from his time at Wisconsin DOT, where he served as a senior payment engineer at Wisconsin DOT and advanced many pool fund initiatives to integrate TSD data or TSDD data into payment management systems. Ali received his PhD from the University of Texas at El Paso, UTEP. Thank you very much, Ali, for presenting in today's webinar Wednesday, and now I'm going to hand it over to you.
Thank you very much, Sherry. Good morning, good afternoon, and welcome to the webinar today. I'm going to talk about a couple of our recent developments, basically, and a couple of ongoing initiatives on the traffic speed deflectometer devices, what we have been doing, what we are doing, and what we are headed to. I'm going to specifically talk about the data quality assessments for TSD data, how we are processing for the quality assessment. A couple of highlights at the network level and project level data applications, as well as a few case studies in different states, and wrap up my presentation with major findings and our research initiatives. First, I would like to acknowledge significant help and support from our team in ARA, Hyung Lee for basically TSD modeling and comprehensive analysis, Abu Sufyan for TSD modeling and data analysis support in different projects, Mertsu for supporting the 3D GPR data analysis and interpretation, Finch Duncan for really leading a lot of work on the GIS platforms and helping us with the linear referencing checks. Vince, Brian Moon, and Ratul for their support with the data analysis as well. So TSDD, the pool fund studies is out there, and a couple of so many states actually are now engaged with the pool fund study to use the data for different purposes, mainly for project, for network level and structural evaluation of the pavement to support the pavement's asset management, and also investigating ways to support the pavement design processes. So many states are already joined the pool fund, and with other states that are investigating the capacity and possibility of using the data for different purposes, including those states outside the pool fund. ARA is now providing the TSDD data analysis support in the different states. In Texas, Georgia, we have been supported. Illinois, Ohio, and Michigan DOT, which are kind of ongoing projects that we are dealing. Before going to the data applications and use cases of the data, I would like to go over a couple of fundamentals of the TSD data, basically to increase and make sure we understand the TSD data properly. Kind of a brief introduction on that aspects. Deflection data. We are looking at the two cases here in these slides. In a case study in Illinois, we are basically looking at two sections of the same road. A few miles away from each other. On the left side, we are looking at the distress section, but not as distressed as the image or screenshot on the right side of the slide. If we look at the deflection and distresses in these two sections as case study, we'll learn more probably about the structural capacity of these two sections. So the maximum deflection on the top of the slides, we are looking in that and these two sections. The sections that has been more distressed on the right side of the slides actually has much lower deflection value in that specific section. So, and the sections on the left side with pretty better the surface condition at least has indicated significantly more deflection, more than 10 times actually. So in summary, the surface distress, as we all know, doesn't tell all the story about the pavement structure within the depths of the pavement. So it's really important to look at both deflection, structural information, and also surface condition. But how the data is measured and how the data is reported and what the TSD data means. Traffic speed deflection devices such as TSD that we are looking at these screenshots. There are different TSDDs by different vendors available in the US. We are looking at one example here. Is basically collecting the deflection related parameters of the pavements. So there are Doppler lasers installing that's beam the truck rear axle right side of the axle and is actually measuring the deflection velocity data. And in this specific the equipment that we are looking, there are multiple parameters that also calculated and reported, such as the surface condition data that is kind of coming from the LCMS lasers and other information such as the right-of-way images, all integrated to a platform called Hawkeye. This information then can be used for different purposes. But let's take a look at a little deeper on the data and how the data and deflection slope are measured and reported. TSD or TSDD measures deflection velocity, the speed of the deflection that is happening under the load on the pavement. So TSD doesn't measure deflection directly. Deflection velocity is measured from the TSD, and we are looking at this slide or screenshot on the bottom of the slide. The Doppler laser is measuring the velocity in the vertical direction, and there is another component of that, the velocity, which is the horizontal speed or vehicle speed of the moving truck. And then the slope of that kind of deflection basing is really considered as deflection slope, which is the deflection velocity divided by vehicle speed in horizontal direction to come up with deflection slope in the middle. Then with using some assumptions and approach and mathematical basically approach, there are ways and approaches to come up with the deflection basing to kind of provide an estimations based on assumptions of the deflection base. But looking at the raw data, basically deflection velocity and deflection slope, what it tells us and what we expect to see from the deflection slope from the TSDD measurements. Here we are looking at the typical or expected deflection slope and deflection basing on the top and on the bottom of this screenshot on the left. And our expectation is to have deflection slope or positive deflection slope in front of the axle and with negative deflection slope behind the axle. The reason behind is that we expect to have deflection values, lower deflection values far away from the axle, right? Far away from the load center compared to the closer offset. And what if the deflection is not showing this expected shape? This can be one example for unexpected deflection slope. with negative deflection slope in front of the axle is one example of those unexpected deflection slope. But what does it mean? If you look at that, if we kind of use our imagine skills, basically the negative deflection slope translates into non-decreasing deflections, theoretically, meaning that deflection far from the load has a higher magnitude from a deflection that is closer in closer offset to the load center, which is not expected. It can happen based on several reasons, really. Discontinuities in the pavement, cracks, potholes, different type of surface distress related issues that can happen. Non-decreasing deflection can happen. The question is that what is that level? How we can use that kind of information to have a better understanding of the data and kind of come up with establishing threshold or guidelines to guide us for evaluating the data quality assessment. So with that brief background or about the TSD data measurement and fundamentals of the measurements and how data is basically reported and integrated, we took another step to devise quality assessment protocol, evaluate the quality of TSDD data. So I'm showing ARA proposed process for TSD data quality check and quality assurance. The first step, get started with the linear reference check. If the data collected, they are tied to the inventory of each state, and that referencing is done correctly, meaning that road names, lane, direction, all the GPS information are correctly reported and tied to the data. That is really the basic step that you want to make sure if the data is reported correct location. The next step, get started with the reviewing of the raw deflection slope. Since the deflection slope is really the raw data coming from the TSDD, we put high emphasis and focus on reviewing the raw data directly. So our steps get started with simulating some sections and some the different pavement sections to get the deflection slope for different case scenarios and comparing the raw and calculated deflection slope reported in the database and kind of using that information to identify unexpected slope, shape, and value, both in terms of the shape of that responses and in terms of the value of the response. The next step is to integrate the TSD deflection slope to come up with the deflection basin. So using the raw data to generate deflection basin directly from the raw data to come up with new sets of deflection basins for further analysis, and identifying the non-decreasing deflection basin as not expected data. And then data QC output will be generated and the summary statistics for each road, for each pavement type, for each section of the road will be generated, and new deflection basin that is passing the quality checks will be generated for further structural evaluation. This is showing one example of those kind of checks. Here in this picture or screenshot, we are looking at the linear reference checks and issues were flagging the entire area that was tested in this example, and with pink points showing the flag areas or potential errors, and the yellow points or yellow lines here basically showing where we didn't observe any errors. And by those errors, they are really referring to if the road names, milepost, lane, and direction and other location features are mismatched, and there is a discrepancy between what was supposed to be collected versus what is collected or was collected, and to kind of identify those flags and recommend correction or further adjustment. On the right side, we are looking at the quality checks of the TSD data, the engineering part. What are the expectation from the data, where it is meeting our QC criteria, where it is passing the QC criteria, and it's called expected data versus unexpected data in this example, shown by green for expected and red for unexpected data. For this specific example, the majority of the sections were passing the RQC with the more expected data compared to the unexpected data. By expected data, I'm not referring to right or wrong. Really, what it matters here is it doesn't follow our expectation. What we expect from the data, the data what it is shown is not really following our expectations. So this is an important step towards increasing our knowledge about the TSD data itself. So this slide, I'm not going to go through the details of that, but this shows one example of the numerical modeling matrix that we use to calculate those expected TSD slope data. We used a different pavement type with different ranges for different layers, different thicknesses, different layer moduli for different layers of flexible pavement, different type of composite pavement, asphalt over concrete, and different rigid pavements were simulated, a relatively wide range of different cases to consider both extreme cases, lower end and upper end of those kind of spectra to capture both cases and to come up with those values that can be within the expected range of the deflection slope response. Then that would be used for checking against the deflection values. This slide shows one example of the TSD data checks I was performing in Texas. Different QC checks divided by main category and subcategories in terms of if sensor recording signal, if raw data was not corrected or was the same as calculated data, expected the slope shape, if the slope shape in front of axle and behind there showing as expected slope value, and deflection value that is coming from different ways and approach from the area under the curve, from ARP method, Greenwood method developed by Peterson, or the deflection coming from integration from raw data, and also the information on the temperature of data collection, if it was within the accepted range or instructed range, and at the end, what portion of the data shows conforming or is conforming to our expectation, basically. In this example, 96.8% of the data were within that conforming range of the values. TSD raw data plots. There is an ongoing developments here to visualize the quality checks. Once we do the quality checks, how we can visualize the data. This is really the preliminary step of this task or ongoing initiative in ARA for showing the data. In this example, we are looking at the blue data points, TSD raw data points, that we didn't identify any issues, and orange or red data points with some sort of possible issues that didn't pass our QC checks. So this is the main purpose here, is to look at the details of each pavement and each roadway type, and kind of with those design drop-down menu on the top of this tool or plotting system to identify what is the source of possible error in that specific roadway, to kind of guide us for understanding the data. So really the next step of this entire initiative is to put this information in a platform that we can look at that and go to that specific data points and identify the locations with the right-of-way images, with other information that is coming from Hawkeye system, and kind of merging this information together to find what is the areas that can be problematic or can have possible errors to kind of guide us to better understand the data in a more meaningful way. Incorporation of the TSD data into Ashdover payment limit design is another really initiative that we are following. It's really at the early stage. So TSD data has been used for network level payment analysis in so many different cases. There are some applications of TSD data for project level analysis. However, there are limited cases and examples. And however, there is no standardized approach to use the TSD data with payment ME design for project level analysis. That really needs a lot of investigations and calibration or some adjustment to the process to basically address the unique features of the TSD data. The loading mechanism and the processing process are completely different with other NDT approach such as FWD. So that needs to be captured and properly addressed when we want to use that approach. But we did the preliminary comparison to see how that can be used. What is the possibility of this? We use different approach using payment ME back calculation tool, modular software, LMOD software, to explore the feasibility of using different tools or back calculation of TSD data and compare it with FWD data. The first bar in this chart shows the FWD back calculated modulus using modulus software. This specifically showing the back calculated subgrid layer module. So we want to show how they are compared for subgrid modulus, which is an important parameter in different designs. We are seeing the data is really different with different methods used. We are looking at very high range of the changes using different methods. With TSD data, the back calculation tool, versus modulus versus LMOD, they're really different from what we observe from the FWD back calculation modulus. We try to refine the data again and use the data another time with performing the QC first. So this slide or this plot is really basically showing the result before doing the quality checks, and then we did another or repeated analysis, but with performing the QC checks. That's specific analysis. The result were in better agreement with FWD, not really exactly the same, but we could see the better agreement for that specific case study. Of course, needs further and more comprehensive evaluation through projects to investigate the possibility of that. But what we are seeing here from this limited case study, basically showing the payment ME back calculation tool showed reasonable agreement with what we can get from FWD, especially after performing the quality checks. To further advance the back calculation of usually we took the challenge really to take it to the next step of how we can specifically consider the features of the TSDD, the dynamic loading conditions and different the sensors that we have, 11 sensors in the newest version of the TSD that we have been used, and how we can consider those type of information as well as viscoelastic behavior of pavement and other frequency and temperature dependent parameters of the asphalt layers or flexible pavement layers. So our TSD expert in ARA, Hyung Lee, developed a tool called DSTL, which is our in-house tool for performing that calculation. This is still being upgraded by Hyung, and we are seeing a screenshot of this tool here. is basically you can put you can define your pavement structure, different layers and different thicknesses with different parameters, um, different coefficients to capture the viscoelastic parameters with deflection, slope calculations. Deflection, basically deflection of slope and deflection velocity calculation. So is pretty dynamic and pretty efficient for doing the calculations of the responses under TSD load. How we can use TSD for back calculation? First, we need to understand how the data and deflection slope is provided to the end users. There are deflection slope, although it's called raw, is not 100% raw. It's basically there is a sensor reference measurements that is roughly 3 meters away from the load center line, 121 inches. That measurement is subtracted from all other deflection slope, and that is reported as the raw deflection slope to the end user. So that is the deflection slope, our reference that we are going to use. So the purpose is to really find the matching layer modulus for that defined pavement structure to basically get the matching responses from DSD or from this modeling versus what is reported or what is measured, right? And in the slide, in the plot on the left side, we are looking at that kind of process. We are looking at the deflection slope that is offset deflection slope, which is equal to deflection slope at that specific sensor subtracted from reference slope. And the purpose again is to get them close to each other as much as possible. So in this example that has been done for deflection slope and deflection basin, and our deflection data showed better agreement with the ESTIL simulated or DMSTIL back calculated deflections versus the other approach or Greenwood deflections that is reported. Looking further details, back calculation versus integrated deflections, we look at a couple of sections in one case study in Texas, and we are looking basically at two different type of sections. The first example is dealing with a less stiff pavement, less robust pavement structure and thicknesses. And we are looking at that and how deflection or integrated deflection are compared with the back calculated deflection. Again, we are seeing better agreement between the deflection from ARP with DSTIL back calculated deflection. In a stiffer pavement, it was a little bit different trend. It was more challenging to get the matching deflection from what is back calculated at this stiffer pavement, and it was the same type of situation for both ARB and Greenwood, and deflection or back calculated deflection really didn't match with what was reported. Another example of the back calculation in different, based on the mileage, where we had both FWD and TSDD data. For that examples, we are looking at base layer modulus, flexible base back calculated modulus, and sulfuric soil back calculated modulus. The blue points shows where we had TSC data, and orange points shows the FWD back calculated layer modulus used obtained from modulus software, and TSC back calculation was done using DST. So we saw in this specific example reasonable agreement between the FWD and TSDD for base and subgrade layer modulus. Specifically for subgrade modulus, it was following the same trend with the overall average, kind of very similar to each other. We haven't observed the same type of trend for flexible pavement or asphalt layer back calculation modulus, and it was not matching with what you're seeing in flexible pavement in that examples. So moving forward with one case study in Illinois of the use of the data for to support the project scoping of the project and how the data was used. That's a different scale. We look at Illinois 17, Kankakee County, the 6 miles of data, and 7.5 million E-cells, 20-year projected E-cells with 4,882 AADT. TSD and 3D GPR data were analyzed to use and support the project scoping. We are dealing with the relatively older pavement, and the plan or the purpose of that project was to use the data to guide the project scoping. In terms of the quality checks, 94% of the data were passing our checks and came up as expected data. So we took further steps after doing the QC. We did our process for temperature correction using Bell's and Ashner approach for temperature correction and load normalization of deflection based on different loads. Different indices were really calculated for different layers to kind of capture those structural integrity of different layers. And then we use the available information with in terms of the traffic information and layer thicknesses coming from the 3D GPR as well as the TSD deflection and load. We incorporate that into the calibrated road equations to calculate the existing structural number and compare it with what is required, what is the design structure for that specific sections, and came up with the structural condition index that is basically comparing those two measures. Those sections with the structural conditioning index of lower than 1 would kind of suggest for a structural improvement. So specific or a specific type of the considerations we incorporate into our analysis. We use the raw data, and instead of the calculated data, to come up with new sets of deflection data that is passing the quality checks, and all other information was coming from basically site-specific information from 3D GPR data. We are looking at a screenshot of the result at the bottom of the slides that shows the surface layer thickness for that section, and we kind of consider all the information and the traffic data, reliability, and the other features of that pavement to come up with that calculations. So in terms of subgrade support strength classifications, we look at that how the subgrade is kind of can be categorized into different categories of poor, fair, good, kind of to get the sense and understanding of what is the condition of the subgrade. For most sections in these specific sections, they're classified into fair with some really limited areas with poor and some scattered points or locations were classified into good structural capacity in terms of the subgrade. In terms of the overall pavement structural condition, the structural condition index, we are looking at these plots, and the sections were classified into poor, fair, and good. And we are seeing that those gaps in between, basically, there were bridges in the locations that were excluded. And this is a specific example analysis, and the majority of the pavement sections were classified as good overall pavement structural condition with this example, and with some areas with structural condition index of lower than 1 and were classified into fair condition. Looking at the surface condition data and the status of these sections, the pavement was cracked with a low to moderate rotting and condition rating score value of 3.2, which was kind of considered as poor surface condition based on the guidelines. And there were a lot of cracks. If you are looking at this example, at the middle of this cracks, and the question was, are these cracks load related or not? And they were we looked at the 3D GPR in more details, and it was we kind of realized there's a concrete underneath, and that can contribute to the development of these cracks in the surface. And in the next step, we look at what is the current guideline of Illinois DOT for using the treatment category selection based on the CRS value. This project was with CRS of 3.2 was basically a candidate for the whole replacement of the pavement with placing a new asphalt or concrete pavement on top. And with using the TSD and 3D GPR data, we kind of realized the structural adequacy of the pavement is not within the range that kind of suggests the need for pavement reconstructions, and maybe a rehabilitation instead of a reconstruction is a more suitable approach to extend the service life of these pavement sections. Case study in Texas, we look at a little bit more details of the data variations, basically looking at the current practice that was used for the data analysis, and looking further at the details of the data, how the data are performing in different type of pay. So we look at FWD data in the sections that we had the TSD data as well, and we look at 5 different segments, or we did the segmentations based on that data. We are looking at SCI, or the DSI tool, which is basically the deflection at load center line minus deflection at 12 inches from the load, kind of as an index to for doing the classification or segmentations, and also subgrid modulus. So we came up with 5 different sections with stiffer and less stiff pavement sections. Segment 1, 2, 4 are relatively stiffer than segment 3 and 5. But let's take a look at what was their behavior for doing this type of the performance of the TSD in different sections. What we saw in this example, the different sections, section 1, 2, 3, 4, 5, we look at the deflection slope in that specific sections that shows kind of more consistent value in that section. We try to identify or calculate the coefficient of variance in that section to come up with the variations of the data along that section. What is the coefficient of variance of the deflection slope within that section? And we realized that for a stiffer pavement that we are looking at this, the higher coefficient of variance were observed at the stiffer pavement, as we saw it in the left side. We compared that with FWD data for the same sections, with having the data collected on the same locations. We were seeing that kind of the much lower, significantly lower coefficient of variance were observed from the FWD data, regardless of the pavement stiffness. And this kind of showed us when we are dealing with stiffer pavements and collecting TSD data, the importance of the data quality checks is really is coming up, and it's really important to look at that further. The comparative analysis for a structural number calculation using different methods, we look at that further to see how a different approach and different constraints that are with different approach are going to be reflected in the calculations. We use ASHTO approach with TSC data and FWD data for comparison, and used road equations, both original and the recalibrated road, to come up with that comparison. What we are seeing here is that basically FWD, the data with ASHTO approach, which is kind of serve as our benchmark for that comparison, we try to use what other approach using the TSD can merge or can result into similar type of values. We saw the better agreements using modified road or recalibrated road equations. That was proposed by FHWA, and that is something we saw a better really agreement with those FW data reference results. So with that, we are the next step of these kind of processes is to incorporate the data into payment management systems. How we can use the data, how we can use the data in a more meaningful way to be able to support the payment asset management, use the correct indices based on different states, their conditions, different environment, of course, climate and different pavement type and conditions, and to use that data. So in terms of the application and use the data, to summarize, what are the applications of the data at network level, and identifying the structured treatments from the TSD data, and then incorporating the data to the PMS, payment management systems, to kind of complete these pieces of puzzle while coming from the structural inputs from the TSD and surface condition from the current PMSs, to kind of upgrade these and update their maintenance and rehab treatment activities for more meaningful treatment selection. At project level, the applications and uses of the data is basically to generate design inputs and come up with TSD indices that can help us identify a specific layer that may not performing, or a structure not performing well, to identify those layers, and also doing back calculation to again support the design. The project level analysis that of course needs more attention and basically more knowledge and the kind of amount of effort to make it happen. Again, there's the ongoing work on doing this in ARA internally, how we can take this to the next level for using the data to support the design project level. So to wrap up what we discussed, our ongoing initiative, back calculation of layer modular using ARA in-house tool with DSD. This is on the kind of on the enhancing mode right now to increase our capability to support the design. Integration of TSD data into HWA payment ME can be really beneficial, and that is the initiatives we are following to support the design of pavement section. And the other really initiatives that was not covered in this specific webinars due to the time restriction was understanding and application of the TSD data, especially for region composite pavement. There has been works done in the rigid and composite pavement analysis. We are trying to understand those and use those, or kind of leverage those kind of experiences to take it to the next level, which needs a really significant amount of effort and understanding to make it happen. Especially the understanding of the composite pavement, because of the complexity of the PCC layer that is overlaid by asphalt is bringing additional or extra complexity to understanding of the data and understanding performance for using. So these are really our ongoing and highlight of our ongoing initiatives that we are trying to advance the current state of the practice. Summary and conclusions: data alignment with the state linear referencing system and inventory is essential before doing any further analysis, and TSD data quality checks is the key pre-processing step to help us have a better understanding of the data, and we can take that to the next level of evaluation of where we are seeing trends between the data and the specific features of those pavements, to guide us to provide guidance for selection of the TSDD routes. When we are going to select the TSD routes, we will get a better understanding of expectation of what to expect from the data. And integration of TSD data in payment ME can basically provide insight at the project level to support the design. That's really needs further evaluations to assess its feasibility. The Hawkeye platform is a powerful tool to identify whether the type of distresses are load related and can be used for different purposes when we are specifically looking at project level type of investigation. Integrated TSD and 3D GPR analysis support. It can support payment design and to come up eventually with cost-effective treatment selection and put the limited resources where it actually needs to be. So with that, I'll hand it over to Shri for next step.
Thank you very much, Ali. That was a very enlightening presentation, but also I don't know if you had a chance to look at the chat board, but the chat board is pretty active as well on this presentation, and we'll get to the Q&A portion pretty quickly, and we have about maybe 10 minutes or so for that. You may now begin submitting your questions in the chat box, and Ali will answer as many questions as possible in the time that is remaining. We hope you enjoyed today's presentation and that you will join ARA on November 19th for understanding and predicting performance in alternate delivery projects by Mike Harrell. And we have many more exciting topics in the works, so please watch your email for updates or visit the Webinar Wednesday webpage, www.ara.com/webinar. So let's get to the Q&A portion of this. Ali, like I said, the chat board has been pretty active, and I've been trying to keep up. I'll just go down in the order, and some of it I may just add some comments of my own. But let's start with Syed Haider, who says, and I think you addressed this a couple of times in your presentation, but this question was from Syed around slide 18 or 19. And if you want to give your thoughts about composite or thick HMA pavements and the quality of TSD data. I think around slide 18 or 19, you were showing how you do assessment of the quality of TSD data. So if you wouldn't mind spending a minute or two to discuss the quality of TSD data for composite or thick pavements.
Yes, thank you, Shri, for bringing that up. That's a very relevant question, Syed. This is specifically important when we are dealing with a stiff pavement, right? When we are dealing with a stiffer pavement that is hard to deflect, what is the solution, right? We want to get some responses. And what if we are getting close to the precision of the Doppler lasers? We are dealing with a narrow band of responses and to measure, and it can be challenging to measure those. It is possible. However, that really needs to be carefully reviewed to ensure is something that we understand it properly. And for instance, when we are doing with other devices, NDT devices such as FWD, one of the options with the stiffer pavement is to increase the load magnitude. And that is something may need to be explored if that is something feasible, right? With the TSDD and with having the same type of loads and having that moved or over the very stiff pavement, we need to be really careful of what we are dealing with and what we are we are expecting to get out. So basically, from my experience, I saw both sides, pavement sections that with passing quality checks, even on the stiff pavements, and I've seen the sections that they were not passing the QC checks on the thicker asphalt, composite, or even rigid pavement. So that is my observation and experience with that specific item that you asked.
Thank you, Ali. The next question is from Rajashekar, and I think it has been answered in the chat already, but I'll just read it out. So if anybody didn't capture that, Rajashekar asks if there are any ASTM or ASTRA standards available for TSDD, asks about field validation and calibration procedure, and I think there is a third part that is approval from FHWA. Cindy Smith responded, there's currently ongoing NCHRP research about validation and calibration. And then Martin responded that there's a draft of an ASTM standard covering TSDD operation currently under review and for voting. So I don't know if you wanted to add anything to that or if that's sufficient, Ali.
Really, yes. Those are ongoing, and since it's the matter of time, really, that we kind of all trying to push the limits and making sure our environment and the community are getting quality data. So there are different needs for generating and looking at that quality checks, which is, we believe, is very important steps to before any further analysis and evaluation. So.
Thank you, Ali. Next question is from Prajwal, and he says FW and TSD usually have different load magnitudes. As such, the back calculated results will be affected. Have you run FWT adjusting the load similar to TSD and do comparisons? So I guess the question is, do you do a load adjustment when you compare an FWD and TSD deflections?
Yeah, that's a very good point, Prajul, and that's valid concern, really. When we are dealing with FWD and TSD, we shouldn't really directly comparing the measurements. We can, but are we comparing apples by apples or no? The answer is no, right? Because the loading is different. One static impulse load in FWD and the other is moving dynamic load in TSD. So they are really different type of loading mechanism. And it's not even that, it's also the measurement is also different. So both loading mechanism and measurement mechanism and the processing is different. The other thing is that when we are looking at, for instance, if you want to compare the deflection on one hand from the FWD is really the maximum deflection that is coming from the time history of the day. That's not the case in TSD. TSD is basically the instantaneous the value or response of the pavement. So comparing these two may not be a direct, they shouldn't be treated as a direct comparison. However, for a modulus of the pavement, since we are testing on the same pavement, the expectation is to, when we are getting the modulus, however way we want to get the modulus, we expect to see agreement between the two values or process result. And they are not going to be the same, right? We all know that. And FWD and TSD, they are different, as we discussed. And the back calculation, that's why we did the back calculation with different methods. Some of them with more precise type of analysis that is considering the exact adjustment of the load, similar to the one that we showed using DSTL. To capture those TSD loading mechanisms, and also use different approach, kind of more simplified approach for doing that kind of comparison. So to address your questions, the adjustment needs to happen, and doing the comparison or direct comparison is not the way that we need to do. So it needs to be considering both the loading differences in FWD and TSD.
Yeah, thank you, Ali. The next couple of questions I think you already answered, and I'll just read it out quickly. Rajshekar asked how to check composite pavements with TSDD, and you've answered your opinion on composite pavements. And Dr. Amar Ayat said, is there any possibility to correlate TSD raw data with raw data from typical FW device? And you just talked about that. The next question, Veera Raghavan Amritalingam asks whether deflection bowl information is collected using different TSDD devices for road network, how should the designer normalize, harmonize the data for analysis? It's a little bit of different twist on the same question, but can you talk about different TSDD devices and any differences, or how should they be compared with one versus another?
So yes. First of all, if the current TSDD that is available, and there are actually multiple TSDDs available, they are really deflection ball is not really collected. Deflection slope is collected, and that is the confusion and complexity that's coming. When we want to use the data or normalize or harmonize the data for analysis, we need to consider that. So, of course, a more simplified way is looking at the with some adjustment and assumptions to go and work with the deflection basing. But we know that deflection basing can generate or introduce some discrepancies down the road, because that's not a really direct measure. So basically what we have been doing was using the deflection slope at really the smaller section and get the modulus, or for design purpose that you're referring to, the designer. And that is the way to go. However, if you want to get a broad estimate, and we know where to get started, the normalization is really to bring down the load and to come up with an equivalent loading the magnitude of the FWD, which is kind of generating some errors with that calculation. So to kind of summarize the answer to that specific questions, load normalization can be done with TSD to consider the load, to convert the load to a reference load, to convert the speed also to a reference speed, and also the temperature. There are ways to do all this type of thing. However, if normalization, meaning to convert it to FWD normalized load, that is where we start introducing some discrepancies with the concept of the TSD.
Yeah, thank you, Ali. We're really short on time, so we're gonna wrap it up here. There were several other questions in the chat, and Abu answered some of those questions, and there were several additional questions that we did not get to. But on behalf of ARA, thank you everybody for joining us today. Today's presentation is being recorded, and a link will be made available on ARA's Webinar Wednesday website early next week. If we did not get your question, presenter Ali has agreed to answer questions for the next 24 hours via email. We just ask that you make sure your questions are not of the consulting nature, and that you understand due to the sensitivity of the topic. Ali's responses may be limited, but feel free to email Ali at the email address amorovatdar@ara.com, and he will get back to you as soon as he's able to. We'll send a PDA certificate to all participants verified by our attendance report as present during the full hour of the webinar, and a copy of today's presentation will also be included. Please allow at least 3 weeks to receive your certificate. ARA is always hiring, and it's a great company to work for. So it's very unique in that it's 100% employee owned. We continue to grow dynamically and are always looking for great people to join our team. So if you're interested in employment opportunities with ARA's transportation and infrastructure offices, please send a brief resume and contact information to www.joinara@ara.com. Thank you everybody again for joining today, and watch your email for our fall webinar schedule. And we hope to see you on November 19th for Mike Harrell's presentation on understanding and predicting performance in alternate delivery projects. Thank you all, and have a great rest of the afternoon.